Hey folks, I'm Chuck Black. We're doing 52 weeks of Python. We are in week number 45, and the topic for this week and probably the one or two after it is going to be concurrency. So we're going to talk about why concurrency is a good idea, how much it benefits us, especially if we're doing stuff related to I/O. In our case, that would be communicating with networking devices. We will look at the advantages, we'll look at the options for communicating using different threads, thread pool, async I/O. We'll talk about multiprocessing. We will discuss the difference between concurrency and parallelism. We'll talk about the global interpreter lock and some of the dangers and perils of doing multi-threaded type stuff. And so we're going to get into that, and we'll even look a little bit at code. Like when I say a little bit, I mean a really little bit, because we're not going to be getting into the actual code until the following lesson. But you can see here I will touch on the code that I've written to do some of these concurrency implementation examples. So hopefully that is of interest to you, and hopefully it will help to teach you about concurrency and get you further down the path towards being a real software developer. So let's get started. Okay, so let's get started talking about concurrency. And before we get too much into it, I wanted to give you a little bit more detailed overview of what we're going to be talking about. Now, what you see here should look familiar to you. This is actually from the previous lessons where we were talking about the database we were running inside Flask with our little mini quakka server. This happens to be host display and host discovery. As it turns out, for this lesson on concurrency, I am going to be implementing host monitoring using threads. And so I will be reusing some of the code that we have written already in our M07 and also before that, where we implemented our mini quakka server. So I will be doing that. But here, if we look at this, then you can see, number one, I like the way that it prints the light green and the dark green, the light green indicating that it's just changed and that things are new. But one of the downsides that you'll see is this over here in my monitoring application. You can see that I'm going to be going through one at a time and attempting to ping each of these devices. If, as it did here at the beginning, the ping fails, then everything waits and we just sit there waiting for something to happen. Now, while it gives a very cool display, it's not the most efficient way to do things. And so we're going to talk about ways to make that better using threads. So that's just a kind of a high-level overview to look for. We'll be using this host monitoring functionality, and we'll be extending it to use concurrency in various different ways. So that's one thing that I wanted to point out. The second thing I want to point out is that you will not escape me attempting to teach you some of the theory about threading, concurrency, issues related to it, the good stuff related to it, etc. So I will, at a reasonably high level, try to teach you what these things are visually. You can see I've created a bunch of slides that we will be going through that talk about the benefits as well as the risks of doing that. And then lastly, when it comes to the actual code, we will be having separate applications, one that does threads, one that uses a thread pool, one that uses async I/O, and I've put some of the common code that all three share into this host common. And so this is where the code is going to be located. And one last thing, I forgot to mention this. Let me see if I can pull it up here. And that is this. We will be using our quakka server running in the background. Now we're going to rewrite this host monitoring stuff, so we don't need that anymore. And we're not going to be looking at things with the display because that's not really what we're working on. But we will be using this Flask mini quakka service, and we could use any one. The one that I tend to be using is the Flask Mongo one, just because it's simpler. We could use the SQL database one as well. I don't believe that I've changed the REST APIs, so you may be able to use the internal memory using the global dictionaries if you wanted to, but I'd probably recommend against that, but you can certainly try it if you like. But I can't speak for whether I changed the REST APIs. If I did, then you would have to either modify that or use one of the database-oriented ones. Anyway, so we will be using this. So when you see me running stuff, be aware that I am running this in the background. I'll try to make sure I point it out every time we do this, but I don't want you to try to run it and you get errors and you don't understand why. Okay, so let's get started. Okay, so let's look at some pictures that hopefully do a decent job of explaining to you exactly what we're talking about when we're talking about concurrency and why networking is ideally suited to take advantage of this type of technology. So in our current situation, that is what I'm doing right here, where I just have an application that does something. It's simple and straightforward, and that's good. But when we're doing something like trying to keep track of devices in a network, hosts in a network, services, other types of resources, if we're doing that and we're doing it in a single thread, effectively just your application running and doing stuff, then what's happening is that you are typically going to be going and querying one thing and then querying the next and then the next and then the next. And so, like in my example here, there's going to be a very slow updating of what information we know and what we learn and what we do with it, such that the entire round trip time, that is the from start here where you see the little space to the point where I finish, is going to be quite a significant amount of time. In our example, in my little example, in my home, I have somewhere between 20 and 30 some devices, so that takes around 30 seconds or more, especially since I have some of these things that you see in red. If I have to wait, this is especially bad, and it magnifies the pain. If I'm doing a ping, pings usually come back pretty much instantly from my devices on my local network. But waiting for these guys that are not responding, that takes, it seems like, forever, and it blocks everything from going forward. So that's why I say here that the elapsed time is going to be the time it takes to do all of your pings, and that's going to include time for all of your non-responding nodes. In my situation with building this Quakka application that is not part of the 52 weeks of Python, but I reference it a lot. When I built that, and I will show you a slide of how I use threading there, which is not the optimal way to do it. I'm just doing it that way for simplicity, and we'll look at how we can improve that. But in the way that I did that, I had at one point in time one of these Cisco Modeling Labs things up and running after I finally got it up and running, and it was abysmally slow, and the devices took forever to boot and forever to respond to requests to connect to them. And consequently, when I was pinging them and they would be so slow, in order for me to make my round trip through all like 6 devices that I had, a few that were in the sandbox and a couple others that were real, by the time I finally got through with that, it would be many minutes. And so my polling, which I wanted to be regularly, was extremely long round trip time. So that was exceptionally bad. Now this host situation is tolerable, right? You don't care that much about hosts, so it's not that big a deal. But something that you do care about, like services that you're monitoring, you really can't afford to have one that's down and have everybody wait behind it for 3 or 4 seconds. So this is the way that it is currently. If we use concurrency, what do we get? Well, what we get is we get the opportunity to do all of these things, as you can see in my little picture, simultaneously. So I'm concurrently pinging every single one of these devices. And consequently, the elapsed time when I do that is going to be whatever the elapsed time is for the longest ping, assuming that I have enough threads to handle, 1 thread per device or something like that. And we'll talk about that later when we if you were to end up with thousands or tens of thousands of devices or whatever. But in general, the elapsed time is going to be the longest ping. The more devices you have, the worse this looks, the worse doing it with a single thread, and the better this looks, because this effectively does not really go up even if you have 20 devices or 40 or 60 or even 1,000 if you can launch 1,000 threads in your Unix or whatever operating system you're running in. Then you have way shorter time to get that information back, whatever you're trying to do to monitor these things. So as you can see, it's way, way better. Now there's different options that we have for how you can achieve concurrency. And don't worry, I'm going to get to concurrency versus parallelism, and we'll look at the different options, etc. So we will be getting to that stuff. Three of the options that I deal with in the code that I've written, and you can see that over here. You can see I have async IO, thread pool, and threads. So these are the three different options, three of the main options that we can look at when we want to do something concurrently. Now, if I'm using threads or thread pool, then I'm going to be using threads, obviously, as you can tell from the name. If I'm using async IO, that has been recently introduced, and it is a way to simulate this type of functionality, but doing it on a single thread. It requires more cooperation from the packages and functionality that exists in Python. Some of it exists, some of it doesn't exist. We will look at that when we get to async IO, but these are the ones that I am using. Now, multiprocessing is another alternative for how we can do this, and we're actually not going to be, I haven't written any code to do that. If you want to know how to do it, it's basically identical to in the code the way you do threads, except everything is using the multiprocessing library instead of the threading library. So for you as a software developer, it doesn't really make much difference to you in terms of the code that you will generate. Now, the ramifications are much greater than the code differences, and we'll get to that in a minute. Hopefully you understand this. I also put down here, you can see all of these things are happening at the same time. So basically, most of what we do in network monitoring is waiting for replies. So network monitoring is ideally suited to this type of concurrency, being able to do all of these things at once. And we definitely benefit from it. I don't know of an example in the real world that is as suitable for doing concurrency as is our networking world. So that's a good thing. So let's talk a little bit about what's going on with these threads. Now, and I'm going to compare and contrast the three different options that we have. So up here I showed you these are the options. Now I'm going to explain these three options in a little bit more detail. So threads are useful for things that are I/O bound. In other words, networking is very much I/O bound in the generic category of I/O. You're going out and trying to get information back. You're expecting a response back, and you're spending a lot of time waiting. And so it's exceptionally good for things of that nature. Other stuff like getting data from a file or doing true I/O, then that is suitable as well. In our networking world, as you can see down here, it's okay for me to do these all at the same time because they're independent entities. Each of these is kind of a discrete operation and doesn't depend on the other. If you're talking about I/O for something like a database, then you need to be a little bit more careful, because if you need to do things in a particular order, then of course you need to do them sequentially, and you can get into problems if you don't do that correctly. But for network monitoring, these devices are pretty much independent of one another. Now that's for monitoring. If you think for a second about modifying configuration in the network, this is one of the ways where things do get complicated in the networking world. So writing configuration data, I can tell you from personal experience, you need to be very careful when you do something like that. So if you're thinking about automating the configuration of stuff in your network, then you probably can do some multi-threading to write that stuff. There's possibilities, but you do need to be careful and watch out. Okay, that's just using threads. Now, I hinted at this, but I'm going to go into it in a little bit more detail now. There's also this idea of a thread pool. Now, if I have 40 devices, I can easily create 40 different threads and run them all simultaneously, as you see here in this picture, and I'm not going to have any problem. But if instead of 40 devices, I have 40,000 devices, can I really create 40,000 different threads? And the answer to that is it depends. It depends on the operating system that you're running on. It depends on the capacity of the device that you're running on. It depends on what the language will allow you to do and what it can handle. So in those situations where it gets to be big, and I used 40,000 as an example, your number may be more like a few hundred. You don't want to start more than a few hundred threads. And I know I've created network simulation tools that attempted to create 10,000 threads and ran into issues on my Ubuntu operating system. And so, yeah, you do need to be aware of it. Then we have something that is called a thread pool. And the idea of a thread pool is it uses threads the same as above, but what it does is it only uses a certain number of threads. And so basically, if you set your thread pool limit at 100, then it will start 100 threads with your first 100 pieces of work. And then as the threads complete, it will pull off a new piece of work for it to do. Our piece of work is basically pinging a node here. It will pull off a new piece of work and it will launch it in a new thread. Now, one thing to be aware of, and I want to make sure you understand this, hopefully that is enough of an explanation and is fairly clear and easy to comprehend. You may be thinking, well, can't I do that myself? If I have, let's say, 10,000 different hosts that I want to be monitoring, can't I just separate them into blocks of 100 and start whatever, I can't even remember the number I used, but let's say 4,000 divided by 100. Can't I use that many threads and just put them onto each of the threads? And the answer is yes, you certainly could, and that would be a possible way to implement it. But the way that thread pools are implemented are as I described them. So think back to what I said. Basically, it's going to launch your first 100 units of work on the first 100 threads, and there is one thread pool that into which these pieces of work get placed. And as soon as a thread is available, then the next unit of work will get placed on it. That's different from our situation where you just created whatever number of threads there are and arbitrarily placed a bunch of your pieces of work, the monitoring nodes in our situation, onto them arbitrarily. If you get unlucky and you have a ton of these red unresponsive devices on one of your threads, then whoever is unfortunate enough to be in that particular thread, be lined up on that thread, is going to have to wait for a very long time. So it can be very unproductive and inefficient. Think of it as going through a grocery store or an electronics store or a home improvement store, where they could do it in different ways, right? You have the aisle that you can go through to pay for your purchases. Sometimes they make you choose which aisle you're going to get in. And if you're really unlucky, like I always tend to be, then you end up behind the guy with 150 items who can't find his credit card or doesn't have enough money or asks for price checks or whatever. So you end up waiting forever. Compare that to the situation where they have one line or one queue, if you use that terminology, and everybody waits in that one line, and as soon as one of the aisles for a checker becomes open, then you get to go into that particular aisle to pay for your purchases. And that's the situation that you have with a thread pool, so it's definitely better than that. Now, async IO is also and all of these are the same as above. It is more complicated to use, but you are only using a single thread. So if you're trying not to use threads, you can use this. Now, I do want to pause for a second. I will tell you that I have implemented async IO, and my implementation is very simple. Unfortunately, for both thread pool and async IO, the examples that I found online, while I guess they purport to be simple and easy to understand, tend to favor complexity over simplicity. And I'm not sure why people do that, especially with a language like Python, which is predicated on the idea of being simple. But I will tell you this is a generic thing, not so much necessarily about this. But when people become proficient at a computer programming language, then one of the things that is a tendency, and I want you to promise me you'll never do this, is the tendency is to use every new snazzy piece of technology and to use it in what in my mind is a more obtuse way of doing it that puts you kind of into the in crowd. It's like using language that only you and your buddies can understand, and everybody else that tries to come in and figure out what you're talking about has no idea what you're talking about. This is a problem with software developers. It's a huge problem with software developers, and that is idolizing of technology for technology's sake. And I see, maybe I'm being too harsh, but I think there's a little bit of that, and I prefer to keep things as simple as possible, but no simpler. So hopefully the examples that I give you, you'll agree, are reasonably simple. All right, let's move to the next slide. Okay, I confess that I went back and forth a number of times about whether I should continue with the slides or hop to the code, and I have decided to continue with the slides so that you have a well-rounded understanding about threading and concurrency in Python. Now, if you are a new person and you've never done any of this before, just the idea of there being threads versus thread pools versus async IO, while the concurrency idea sounds cool, this is starting to get to the limits. I'm about to go into something that's going to go even further beyond the limits, but I ask you, if you are new, just to hang in there and to understand at least the concepts on the surface so that you understand kind of what's going on. And some of this stuff will be more easy and apparent than others, but just bear with me. And if you are brand new and you don't want to go through this, then yeah, just come back when I'm going through this actual code. So let's talk about a few things related to, well, this is more a threading issue, but concurrency in general in Python. Now, the thing that you'll hear about over and over and over again with respect to Python is this thing called a global interpreter lock. And people will say, well, Python can't really do multi-threading, and it's no good for threading because of this global interpreter lock. And what is the global interpreter lock? Well, basically it is something that is going to block threads from running simultaneously. So you would say to yourself, why then would I even try to do things concurrently? Well, it's no problem if you're doing IO like we're going to be doing. So you're doing stuff to the networking, not an issue. It's perfectly suited. Let me go through the slide here in the bullet points just so that we have a understanding of it. Why is there a global interpreter lock in Python? The reason is because Python's internal implementation, that would be something that is called CPython, isn't thread safe for doing some of the things that we would like to do. You can Google online, why does Python still have a global interpreter lock, etc., etc. That's how it was built, and it persists to this day. So just understand that it's there. What actually happens with the global interpreter lock? Well, in general, and this is kind of a high-level description, the global interpreter lock is going to prohibit threads from making use of multiple CPU cores. So we live in a day where there's multiple CPU cores, and we should be able to push processing execution elements through these multiple cores, but the global interpreter lock is going to block that from happening. And the actual result of this is that if you do things that are CPU bound, that means they're doing stuff like numerical computation or string in-memory string manipulation, then you're going to find that your multi-threaded solution may actually run slower than a single-threaded solution because of the overhead of the global interpreter lock. So actually you just have to be careful of what you're doing. Now, like I said, for our type of environment, if you're a networking person or if you aren't, then environments that are IO bound, then these are perfect candidates for being enhanced in terms of their efficiency by using threads. So be aware of the global interpreter lock. Don't try to throw threads in everywhere where they don't belong, but just be aware that it exists and be thankful that our environment is such that it's not really a huge effect for us. If you are concerned about the global interpreter lock, one thing that you could do is you can choose multiprocessing rather than threading. Remember, if I go back to this slide up here, I mentioned about concurrency. We have threading, thread pool, async IO. You can also consider doing something like multiprocessing. And as I said, the actual libraries or packages that you use for doing this look almost identical between threads and multiprocessing. The difference is in this picture, you can see these little individual processes are going to have their own execution instance that's greater than this threading. I've tried to draw these pictures appropriately in these situation here. Let me do this picture. It's a little bit better. You can see these threads are running inside this monitoring process, and in the multiprocessing situation, we are creating little processes that are actually running and are independent and on their own. They have their own data and they are able to run separately, and so you don't have to worry about the global interpreter lock, so that's a good thing. Then, as I mentioned, they are separate independent processes, so if they're just doing things like pinging, that's perfectly okay. Now, there is a slightly greater overhead. A thread is a lightweight process, so a thread has a little bit of the computer sciencey process type stuff going along with it, with its stack, with its control pointers and all the other stuff that goes on. Multiprocessing in Python, there's a little bit more going on here. It has its own memory entirely, so you're not sharing any memory, but consequently, there is higher amount of overhead. So I mentioned that. So you can use multiprocessing. I did not create an example in the code over here that's using multiprocessing. Hopefully that's okay. If you do have multiprocessing questions, feel free to let me know about them. So you will hear these two words mentioned, concurrency and parallelism. Now, at a high level, just in normal vernacular talking about stuff, we would use these two words kind of interchangeably, meaning that you're doing stuff at the same time, basically. And so that is generally true in the English language. However, the definition of these two has diverged, and there's a nuance, I guess. You could say they're significantly different, or there's nuances, or whatever you want to say, but people have descriptions and comparisons of these two, and so I figured it would be useful for me to describe the two, what people are talking about when they talk about parallelism versus when they talk about concurrency. Probably the best quote that I saw, I pulled off of somewhere, I can't remember where it was. Concurrency is about dealing with lots of things at once. So the key word here, dealing with lots of things at once, while parallelism is about doing lots of things at once. Now that may seem like just semantics of the language to state that, but basically if you look over here at this situation, this is my concurrency situation. I am dealing with a lot of these external nodes by monitoring them, and I'm doing it all at once. I create all of these threads that do it, that allows me to deal with them at once. And in difference to that would be parallelism, which I'm trying to demonstrate here with my hokey little arrow that's showing that it's doing stuff. It's basically trying to do a lot of things at once. So the usual example that they give for parallelism is that you're doing like mathematical calculations, and wouldn't it be handy if I could just calculate square roots of 1,000 numbers all at the same time? So you spawn 1,000 threads and start them and calculate square roots or whatever it is that you're doing, and then you find out that it actually took longer than if you had just done them one at a time. That's because of this thing right here, this global interpreter lock. So if you're not doing stuff externally, I/O related. And for us, networking is I/O. It could be database access. It could be file access. It could be a number of things. If you're doing this, then you would call it concurrency, and it works very well. If you're trying to do stuff like this, that's what we would call parallelism. And on modern computers, you could take advantage of multiple cores in order to do this. Unfortunately, Python doesn't allow you to do this. So that's a downside. Now, I talk about how cool it is that we're dealing with these external entities. In networking case, we're dealing with networking devices that we're communicating with, and that's good. And for the most part, our threads have local memory, which would be memory that is associated with our local piece of execution, our execution work that we are doing. If you think about a function, it would be local variables within the function. As long as we're dealing with those things, then we are okay and we don't have anything to worry about. However, if we do have this shared memory that we're all trying to do something with, and multiple of these threads are trying to access it and do stuff to it at once, then you can end up with situations. If you recall our Flask situation, we only had one writer to each of those dictionaries, those global memory dictionaries. So we ended up being okay. That was running on independent threads, not because we created them, but why? Because every request to Flask is running on its own thread. That's how web servers work. When somebody makes an HTTP request, there will be a thread that will service that request. And so that thread is coming in and doing something. Because we only had one host monitor modifying the host table and one device monitor modifying the device table, then we were okay. When we got to a situation like we did when we went to our database stuff, especially for Mongo, if you remember that one, I created two different applications. One was host monitor and one was host scan, and they were both writing to that to the host data. But because it's stored in a database, databases are thread safe. So this is internal memory that I'm referring to here. Databases, that's why we moved everything to the database. Perhaps this helps you to understand what we were talking about before. So local memory, which is accessible just by the thread, is safe, but shared memory is not. Now here's a word that you may that you may hear and want to understand what it is. Atomicity, atomic, these things, this word is used to refer to operations on data in computer science that cannot be interrupted. And so what we would like is, for example, if I have an index that's going from 1 to 20, if I increment that index from 1 to 2 and then from 2 to 3 and 3 to 4, we would like that to be an atomic action. And in actuality, in computer languages in general, it is not. And that's what I'm going to describe to you here. Now, I don't have a slide for this, but I want you to try to pay attention and follow along with me. When I want to increment a variable, let's say the variable I, when I want to increment it by 1, it's a 3-step process. The first step is to read the current value of I. The second step is for me to locally increase the value of I by whatever I'm incrementing it by, let's say by 1. And the third step is to write it back into the memory location that is I, or in Python, since everything's an object, to actually create the new object, which I will then point to. So it is a 3-step process. If you have multiple threads and they are all, or at least 2 of them are trying to access I, then you can see if I have read the value of I and its value is 1, and I want to increment it, so I begin my process of incrementing it, and some other thread comes in and also wants to increment I, and so it performs an increment function. It reads I, and I is going to be the value that it was originally, and you end up missing an increment in that situation. So that is one of the reasons that we need to be especially careful with shared memory when you have multiple threads. In the code that I'm using, I actually am I'm not even writing out the data after I've read it in, so there's not really an issue related to that. But if I was writing it, I would want to be writing it to a database. Now, this is kind of an oversimplification of things, and I don't want to trivialize it. Python does not answer all of this by the global interpreter lock, but it gets around a lot of this issue internally by having that global interpreter lock. All right, here's the last thing that I want to point out to you, and that's this. For those of you that understand a little bit about Quakka, this is not my mini Quakka. This is the actual Quakka application that's out there in a separate repository. The question, if you were to say, does Quakka use threading? And I would say yes. And then you would say, okay, well, that's cool. You're doing this stuff all at once, right? So let me get back to this bit. So you're doing this, right? And I would say, no. So the threading that I implemented is for another purpose. And so if I was going to make this a real product, I would do a further level of threading inside of it. But what I have, because remember the difference between our mini Quakka. I'm going to go up here and we're going to look at this mini Quakka picture. I have all of these applications running externally. And so I didn't need to do any multi-threading because host monitor is an app, device monitor is an app, host scan is an app, service monitor is an app, and I ended up creating it on our little 52 weeks of Python train that we're riding on, and I thought that was kind of fun to do and cool, and that's the way I did it. But a long time ago, when I implemented Quakka, I implemented all of that functionality inside our Flask service. Now that we can argue about the advantages of one versus the other. I'm not going to go into that right now. But in order to do that, remember that our Flask application, sorry, I'm going to go back here. Our Flask application basically just sits here and waits for REST stuff. There's not any execution going on all the time in the background. If I wanted there to be execution, I would need to create separate multiprocessing processes or multi-threading threads. And in this implementation here, I haven't done that. But in my Quakka implementation, I need to do that because my Quakka app, the service, is actually going out and it's monitoring devices, it's monitoring compliance, it's monitoring hosts, and it's monitoring services. So it's doing that. Now, pause for a second. Let's talk about this host monitoring thread. That is one thread, okay? Are y'all with me? That is one thread, and it goes through and monitors the hosts like this, one at a time. It doesn't create separate threads for doing it. If I was going to spend a little bit of time to improve Quakka, I would go and I would implement it like this, either with threads or with a thread pool, because I happen to favor those. But for any of you that are interested in Quakka and have been comparing it to what we're doing and understand what I'm talking about, this is how I'm using threads. I have a fixed number of threads that I have created that are performing these functions. If I wanted to do simultaneous monitoring of my host and of my devices, which would be an intelligent way to implement this in the real world, I would want to be using threads or thread pools or multiprocessing or maybe even async IO in order to do that. Okay, that's all the slides. Now the next thing we're going to do is look at the code. I suspect that will be in our next lesson though, but let me close this part of it for now. Okay, so we've run out of time to go through the code in detail, but I did want to give you a little glimpse at what we will be looking at in the next lesson. Here is host monitor threads. That's the host monitor application, but I've added threading. This one is the same thing, but I've added thread pool. This one I've added async IO. The highlighted area is the code that implements threading. Here I have to manually create, start, and then collect them when they're done. Thread pool executor does that for me, so the code is shorter. Async IO, also the code is quite short. Up here, if we look at the code to do a ping host, which is what we call, it's pretty much the same as host monitor, except it's a little bit simpler. With host monitor thread pool, again, the ping host is the same. Over here in async IO, we have ping host, which is what does the old normal way when I do it one at a time for comparison. To do the async IO, I had to rewrite this function to be ping host async, and it has some async stuff in it. But that's what we will be looking at the next time. So hopefully this gives you a general idea that it can be pretty easy to implement. And yeah, this is what you can look forward to. Hopefully it will be interesting and informative as well. All right, so let's quickly review what we talked about. We talked about using things with a single thread is slow because you have to go through one at a time, and especially if things are not responding, that can take a very long time. Doing things in a concurrent manner is much better. If you use something like threads or thread pool, then you can launch all of these at once and get all the responses back, and the elapsed time is way faster. The options that we had discussed in this lesson were threading, using a thread pool, and async IO, which is a newer thing. And we also offer the option of doing multiprocessing, which we'll see a slide for in a minute. We talk about the difference between these things, what a thread pool is, what async IO is, and how it only uses one thread. Then we talked about this dreaded global interpreter lock. We talked about the reasons for using it, what it does, and what the ramifications are for you. The good news, though, is especially if you're in the networking world, things that are IO bound don't suffer from global interpreter lock issues, so that's much nicer. We did touch on multiprocessing and the fact that you don't have to worry about the global interpreter lock. There is a little bit more overhead because these are independent processes and you don't share memory, but you can get around that GIL. We talked about the difference between concurrency and parallelism, and how with concurrency you're dealing with lots of things at once, and with parallelism you're trying to do a lot of things at once. And this picture kind of shows concurrency here, which is kind of nice, going out to all these devices at once, versus parallelism, trying to do all of these things internally, like mathematical computations, at the same time. This does not work in Python with threading because of the global interpreter lock. So you just need to be aware of that. That's the difference between those two. We did say that you do need to be aware, in spite of the global interpreter lock, that you can have issues with shared memory when you have multiple threads. That's why I talked about this when we talked about Flask and how all the REST requests come in on a separate thread. And if you have shared memory, you can end up with issues. The issue really is that operations for writing data are not atomic, and so you need to be aware of that. That's why we moved everything into a database rather than shared memory. Lastly, in terms of the slides, we talked about how Quakka uses threads. We're not actually utilizing the stuff that we just talked about, but we're rather, for running inside of Flask, we are actually starting separate threads that do each of these type of monitoring, but we're not doing the individual device monitoring on separate threads, which we probably should be doing. And then we talked a little bit about the code that we will be looking at, and gave you a teaser about it. And that's basically what we talked about. Hopefully it made sense. If anything is unclear, please give me a question or write me a note to say you got it or you didn't get it, or whatever. So yeah, I hope that explains threading and concurrency a little bit. Thanks for listening.